So I have here a small amount of notes, and that's all I have for a week in terms of new material. Yeah.
I might be, it's not sure, but I might be getting a call that I have to take, so if it happens, I'll just look up.
Okay, thanks for warning. Yeah, okay. All right. So then, other than that, we'll see if anybody has some homework questions. So I guess really, for Thursday, that's all it'll be. So if you don't have homework questions for Thursday, then why be here? But I'll show up regardless and see who's here. Okay. So now we're getting into a new chapter in the notes. Okay. Elliptic equations. Now, a lot of examples we dealt with the Poisson equation. And that's going to continue to be a focus into this next chapter. But the focus in this chapter, as opposed to previous ones, is about when you take a PDE like Poisson's equation and you discretize it and wind up with a system of linear equations, AU equals F or something like that. What are some approaches to solving that system? And there's discussion of that, for example, in for instance, Math 461, 561. My class next semester, Math 610, will also get into that. So this chapter will basically be a survey of certain methods that are used for not necessarily linear systems in general, but the kind of linear systems that arise from PDEs, because efficiency is essential because we're dealing with systems that can be quite large, but also the matrix in question may be ill-conditioned, which generally happens with dealing with PDE. So that's something to consider. So, the look at Poisson equation, not the usual minus u x equals f, but 1D, but 2D. So we have minus uxx plus uyy equal to f. And the domain omega will be, square, x and y between -1 and 1. And let's take the homogeneous Dirichlet boundary conditions, as usual. Okay. Now, we step back temporarily to the familiar 1D problem for minus u x equals f on -1 and 1 with homogeneous Dirichlet boundary conditions at the endpoints. You discretize this PDE, and you get a system K1D with a matrix times U is equal to F, and we know what K1D is from this case because we've seen it before. So we have the tridiagonal matrix. From the center difference. I should mention, this matrix is tridiagonal, but we can say more than that because on each diagonal, the entries are the same. But, well, it is symmetric too, but even besides that, the fact that each diagonal has all the entries the same, which is not necessarily true for any symmetric tridiagonal matrix. Like these entries are allowed to be different. For symmetry, as long as these entries are the same, What about being the same down a diagonal? That's called a Toeplitz matrix. So this is symmetric, tridiagonal, and Toeplitz. So general Toeplitz matrix is one in which along any diagonal, all the entries along that diagonal are the same. And there's a lot more known about Toeplitz matrices, like how to compute determinants, eigenvalues in certain cases, things like that. Okay. Now I should emphasize, this is what the matrix we would use if we're using finite difference. We could use a different differentiating matrix. As an example, one such matrix that we have seen for homogeneous Dirichlet boundary conditions is a Chebyshev matrix. So some matrix that is a discretization of minus Laplacian by whatever means. Okay. But we want a matrix for the 2D problem. How do we get that? Well, once you have a 1D matrix, whichever one you're using, it's very easy to get the corresponding 2D matrix. So you take your one-dimensional matrix, and then this symbol, the times of in the circle, is called the Chronicle product. So we take Chronicle product of K1D of identity to discretize one of these differentiation operators, either UXX or UYY, and then you do it in the opposite order, identity Chronicle K1D, to get the other one. I'm being intentionally vague as to which is which, because it depends on how you order your grid points in your two-dimensional grid. For example, you could, because your solution, doesn't matter whether you're 1D, 2D, or any number of dimensions, you're still solving a system of this form with matrix times vector equals other vector. And if you have a function on, say, defined on a two-dimensional grid, you might think, oh, it makes sense to treat that discretized function as a matrix because it's natural to arrange your grid points like a matrix. And yeah, you can set it up that way at first, but you still have to reshape that matrix into a vector to solve this system. And then once you have your solution, then if you want, you can reshape it back into a vector, like for visualization purposes. Okay. So you consider ordering of grid points. When you're in two dimensions, you have a couple options. You can do x1, y1, then x1, y2, x1, y3, down to x1, yn. So then you exhaust all possibilities for x1. Then you go to x2, y1, x2, y2. So that's one possible ordering. Another possible ordering is x1, y1, x2, y1. So now the y is held constant. Then you start again with y2, etc. So which convention you use affects which one of these is for UXX and which one of these is for UYY. Okay. I do want to talk about that part more, but I also need to explain what is a Chronicle product, because how however many linear algebra classes you've had, you probably have not seen this operation. Okay, so in general, A Kronecker product B. So if A is M by N and B is P by Q, then Kronecker product is a matrix that is MP rows times NQ columns. So you multiply the rows in each, you get the rows in the product, and similar for the columns. And how you get the entries, it's actually easier to describe as like informally. Think in terms of taking B and tiling it. So you're making a M by N tiling of B. But each tile is multiplied by the appropriate entry of A. Okay. So that's what the Kronecker product looks like. I guess another way of thinking about it is, if you start with a matrix A, and you take in each entry of A, you put a B in there. So it's not a terribly computationally expensive operation, not like, for instance, if you were using matrix multiplication to create a matrix of this size. So that would take more work. And especially if the matrices involved are sparse, like these would be if K1D comes from finite differences, but certainly the result will also be sparse. Okay. This for 2D readily generalizes to 3D. You take K1D, product product with identity twice, and then two more terms like that with different orderings. But each term has a K1D and two identities involved in a product or product. So one of these is for UXX, one for UYY, one for UZZ. So this is the easiest way to get the matrices, like if you're doing this in Matlab, because Matlab has a function cron that implements the Kronecker product, so you can just use that. Okay. Questions about anything I've written so far? Now, since I was mentioning how you order your grid points before, I'll talk about how it works in Matlab when creating two-dimensional grids using its functions and therefore proceeding in the most straightforward way possible. All right. I'm going to consider the case of the domain as a square and equal spacing in X and Y. But certainly this can be adapted to the case of like a rectangle or different spacings. So I can let H equal, well, we're going to say domain is for X and Y between -1 and 1. So I let H be 2 over n plus 1, because the width of your domain in X or Y is 2, because you're going from -1 to 1. And we want n grid points in the interior for each dimension. So then I'll define xi to be I times h. So now I have, that's my one-dimensional grid. For the interval -1 to 1. So I want to go from that one-dimensional grid to two-dimensional grid. All right. So a way to do that in Matlab is, if I make a vector x, then I can feed that to mesh grid. So you just supply as inputs a vector of x's and a vector of y's. So your one-dimensional grid for each. In this case, I'm on a square, equal spacing. So you can just use x for both arguments. Okay. So then, since x is an n vector, x2 and y2 are going to be n by n matrices that have the coordinates, the x coordinates and the y coordinates of all the points in your two-dimensional grid. And I can show you what these matrices look like. So first column of the matrix x2 will be every element equal to x1, first grid point in x. We have x2 and xn. Which makes sense because as going to left and right, from left to right, that's changing x, not y. So first x coordinate, second say x coordinate, and so on. Whereas y2 will have whoops, wait, that's totally wrong. All right, so here each column iterates over the y value. So whereas in x2 every column is constant, in y2 every row is constant. So your grid points would be x1, y1, x1, y2, and so on. Going down the first column, and then over to the second column. x2, y1, x2, y2, etc. So suppose you have a Matlab function for your function f in Poisson's equation, so minus Laplacian of u equals f. I'll make one up. So your function f of xy, I'll just say it's equal to sine pi x sine 2 pi y, and I made this function, I chose this function because when x or y are equal to plus or minus 1, the function will be 0, therefore it'll, so this would satisfy the boundary conditions. So how you could implement this in Matlab, I can say f is equal to @, and I define f to be a function handle with parameters x and y. And x and y, I should assume that they could be numbers or vectors or matrices. And then I can put this formula in. So sine pi times x dot star sine 2 times pi times y. Because whatever x is, sine will have the same size as x. And this sine will have the same size as y. And x and y also should be the same size. Again, it could, but because it could be numbers, vectors, or matrices, I need to dot multiply. So I'll do component-wise or entry-wise multiplication. Yes.
I just lost a bit. What was the @xy doing?
Oh, so this is MATLAB syntax for defining a function handle. It's actually called an anonymous function when you do it this way. The other way to define this function, of course, you can always create an M file and say, function z equals f of x, y, and do it that way. But here you can just type this at the prompt. So we're defining very short, simple functions, one-liners. This is a good way to do it. Okay. So when you're setting up your system equations for Poisson's equation, so matrix times u is equal to f, so you define this function handle f. So then if I use RHS, right-hand side, to refer to the right-hand side of your system, I could do this, f of x2, y2. But since x2 and y2 are the output of mesh grid, this is going to be a matrix. But I need a vector. So, so this matrix has to be reshaped into a vector before I can use the backslash with my matrix K2D to solve a system. The easiest way to reshape into a column vector, which is what we want here, is to do this. It's just a nice shorthand. Also use a reshape function, but certainly this is easier. Okay. So then, so now it's a column vector. You solve your system of equations. The solution u will also be a column vector, but then you can use MATLAB's reshape function to reshape that into a matrix if you want to display the solution as a surface. Now, very important about reshape. Two-dimensional arrays. That's just a conceptual device for us. That's how we see these things. But memory is inherently one-dimensional. So the elements of a two-dimensional array are laid out linearly in memory. So how are they ordered? Do you store all of the elements in the first row first and then go to the second row, which is called row major order? Or do you store elements first column and go to the second column? In other words, column major order. Different languages use different orders, which it's nice to complicate matters. C and C++, for instance, use row major order. Fortran uses column major order. At its lowest level code in Matlab is in Fortran. Therefore, Matlab uses column major order. So if I take a matrix and have Matlab reshape it into a column vector, it will go column by column. In other words, the natural way for Matlab to order points in a 2D grid, if you're using mesh grid and then reshape, it's going to be this ordering. So, okay. Why? Because Fortran uses column major ordering. Therefore, Matlab does too. And I must confess to embarrassment that I don't remember, even though I have an edition of my book for Python, I don't remember what ordering row major or column major that Python uses. I guess that's something I would have looked up back when I was doing the book, and since that came out over a year and a half ago, I've forgotten. I don't like Python very much, but I felt the need to write it.
Probably the most complicated one, just for this.
Well, that would be par for the course with Python.
Yes. I don't like it either.
Sorry if there are Python fans in the room. Okay. Haven't touched it yet?
I have, it's just not enough to
Yeah.
have an opinion about it.
Okay. Probably better off that way. I wish I remember Python being more flexible about it. Oh yeah. Okay. When you're creating a matrix in Python, there's this parameter you can use to specify either row major or column major, but the default is row major. So yeah, I knew it'd be different from Matlab. Okay. So things to keep in mind when working in two-dimensional problems in Matlab. Oh, we only have one homework problem that's 2D. That's problem number 7. So it'll come up there. Questions about any of this? Okay, I should mention that using either kind of ordering is, but because you're dealing with points consecutively, whether you're diverse rows or columns, that's called lexicographic ordering. And you might think, well, what other ordering could you possibly use besides this? Another ordering is called a red-black ordering. It's like a checkerboard of red and black spaces. So if you have designated alternating points, red versus black, and then you group all the red points together and the black points together, that could be advantageous for using Gaussian elimination of certain matrices to reorder rows and columns like that. We won't really get into that, but I just want to mention that that's something that's out there. Okay. Just because it could give a matrix a nicer structure. Okay, now, okay. So suppose we're using finite differences. So one dimension is using the center difference for uxx and also for uyy. So, right, so using a one-dimensional center difference, in conjunction with Chronicle product, to go to 2D, that leads to a 5-point stencil for the Laplacian. And I'm pretty sure it's something I mentioned earlier, 5-point versus 9-point. I'll draw it again. So you're using these 5 points. So here you have a center difference in x, and then these 3 points. Use the center difference in y. Now, in that case, what we have is, so the error. I'm going to use this notation, Laplacian symbol with a subscript of 5 to indicate the 5-point stencil. So that is equal to the exact Laplacian plus an error term, which is 12u, so 4/3 of u with respect to x plus 4/3 of u with respect to y. Each one of these terms coming from the error in a one-dimensional center difference. So we're just adding the errors from x and y together. And then additional error terms that are order h to the 4th. On the other hand, suppose I use the 9-point stencil. That includes these 5 points and then the 4 corners. So the circles are for 5 points. The circles and the x's together make up the 9-point stencil. What happens in that case? Get a different error formula. Okay. At first, it might not seem like much of a difference. In fact, these 2 terms we have in the 9-point error, but we have an additional term. Okay. Now, what I can do with this, that's the same. If I break up this term of 2 uxxyy into one of each, so then I have uxxxx plus u yxx plus uxxyy. Using the fact that under certain reasonable continuity assumptions, mixed higher order partial derivatives are equal. So what I'm going to do here is I'm going to think in terms of factoring out a second differentiation with respect to x. So if I keep in mind that xx here and xx here, and for these terms, I think in terms of factoring out a yy, in both cases, what's in the parentheses is the Laplacian. So I take Laplacian xx plus Laplacian yy. Well, that's taking a Laplacian of a Laplacian. Now here's why that matters. We're trying to solve Poisson's equation. The inner Laplacian, we know what that is. Minus f. So the error in the 9-point stencil be minus h squared over 12 Laplacian of f. So of course you never know the error exactly, because if you knew the error, then you can always get the exact solution. But in this case, we do know the leading term of the error. So this actually comes up in the homework, problem 1, for the problem 2, part C. We're doing what's called a deferred correction. Now that is a 1D example. And the funny thing is, you take a one-dimensional center difference, the most straightforward generalization of that to 2D is a 5-point stencil. But a 5-point stencil, the error is not of the right form to do some trick like that. But the 9-point stencil is. Okay. So, well, first, any questions about what happened here? So how I'm going to use this, and how you will also use it in that homework problem, is as follows. But to exploit this knowledge, we'll solve this modified equation, minus Laplacian of u is equal to f, with a term added on, h squared over 12 Laplacian of f. And we can see why this works by looking at the local truncation error. Okay. That's the, because what we would do in discretizing is, I should put a 9 here, we're going to use 9-point stencil for this. All right, so the 9-point stencil of the exact solution minus the right-hand side, the entire right-hand side. So I'm using a definition of local truncation error, matrix times exact solution minus right-hand side. So this is minus tau back then. Okay. But now I'm going to substitute the error expression I had earlier for the 9-point stencil. Well, that would be the true Laplacian minus 12 plus unit F plus additional terms that are order 8 through 4, and then minus this other stuff. Okay. And what happens is, well, Laplacian of U is equal to minus F, because U is the exact solution. Well, everything cancels, except the term is order 8 through 4. So the result is, by modifying our system, our discretization, by adding, really what we're doing is we're subtracting off the leading error term, that you get fourth order accuracy. Okay. And this is an example of what is called deferred correction. Remember many years ago, I studied a conference and the speaker was giving a talk on deferred correction. So he opened his talk by saying that this talk's on deferred correction, so if there are any mistakes, I'll fix them later. Questions about what happened here? Okay. Now, when you're discretizing, whatever PD you have, to obtain for instance, Poisson's equation, to obtain a system that's dependent on some grid spacing, so AH equal to FH, whereas the superscript of H is meant to indicate dependence on the grid spacing that you're using, whatever that might be. What is the best way to solve this system? I mean, you learn certain methods in linear algebra or intro to numerical analysis class, like using Gaussian elimination, or if the matrix is symmetric, positive, definite, which Cholesky factorization, things like that. But and actually, yeah, in 461, 561, I would have covered a few iterative methods. So just to catalog the many options that are available, if using a spectral method, that's choice to use some method that's based on a solution method that's based on the fast Fourier transform. And that's true whether you're dealing with periodic boundary conditions, so your solution has a Fourier series representation, or if you're using Chebyshev discretization, because there's a close relationship between Chebyshev polynomials and BFFT, or more specifically, a discrete cosine transform. So for spectral methods, something involving FFT is generally the best choice. But otherwise, if you're using finite difference or FEM finite element method, or we'll leave anyone else, or finite volume method. There's a whole other category of methods for PDEs that people in this department work on, and are called meshless methods. So they're not as well known or highly adopted as these. But Dr. Chen Dr. Tian, Dr. Zhu have all worked on those. So I guess mainly because of Dr. Chen, but who's one of the leading figures in that area. But Dr. Zhu does a lot of work in finite elements. Dr. Tian does a lot of things. I've seen her work with a wide variety of methods. So, and spectral, well, that's me. Although before coming to USM, I did a fair amount of work in finite volume. So, okay. So for other kinds of discretizations, there are a number of options available. So we have direct methods. Main one being, of course, Gaussian elimination. So any solution method that's based on elimination and substitution. If a matrix has a certain structure, then you might not be best to use Gaussian elimination. For example, if a matrix is symmetric, you should use the LDLT factorization. If it's certainly also a good choice of matrix is symmetric positive definite, in which case you can also use a Cholesky factorization. Okay. So sort of these are most general purpose methods. Okay. We also have what are called stationary iterative methods. These ones are covered in 451, 561, like Jacobi, Gauss-Seidel, etc. And SOR was the number one. The word stationary comes from the fact that a lot of these iterations are based on what's called a fixed point iteration, which we've also seen in the context of root finding for solving nonlinear equations. Okay, and these kind of methods are an essential ingredient in a type of method I'll be covering later called multigrid. So multigrid is exactly what the word suggests, where you're solving problems on grids of different resolution. And the key ingredient to get an approximate solution to work with before you move from one grid to another is often one of these stationary iterative methods, because they're quite simple to implement and they have some pretty nice convergence properties. And then another category method is non-stationary. Also known as Krylov subspace methods, the ones that don't really fit the form of a fixed point iteration. The most popular of these is CG, or conjugate gradient method for symmetric positive definite systems. The method is so popular they threw a party for its 50th birthday. Also for more general systems, GMRes, so generalized minimum residual method. Also there's biconjugate gradient for unsymmetric systems. So I'll be spending some time on each of these in the coming weeks. I think it's the next 2 weeks. Krylov subspace methods I will spend some time covering in next semester in Math 610, if you're interested in taking that. Okay, so all right, so that's the stage for what I'll be covering next. All right, well, got through a whopping 2 pages of notes. Or at least the game is good, just the normal. Okay. I give up. All right, more questions. Okay, oh yeah, I guess you indicated earlier, but you wouldn't have any, but review?
Okay, so the latter part of question 1,
Yeah,
where we are supposed to show that the real part of R1 is imaginary, sorry, it's negative.
yeah.
My question is, are we supposed to put a boundary on the D?
Are
we supposed to restrict it?
Okay. I don't recall if a problem stated a restriction on D. I think there is an assumption about it. Okay. Do you have your work with you? Just to refresh my memory about certain things. Okay, so, okay, and then K can be anything, so this comes from the telegraph equation. Okay. Okay. All right, so the constants involved, LC and GR. Okay, based on what I've seen from a derivation of a telegraph equation, it looks like it is D is supposed to be positive. Okay. Yeah, it is. So, okay, yeah, because otherwise, we might have a bit of trouble there. So, yeah. Okay. Anything else for homework or?
Yeah.
Oh, okay. Is progress being made in homework? Okay, all right, that's good. Okay. Because I was gonna be like, we're getting close to halfway. Okay, in that case, bring your homework issues and we'll see if I see anybody here or not.